continue. Let us consider the form of the differential balance given in equation 10.1-3. dm over dt equal to m in plus rg minus m out minus r cons. Cons refer to consumption. The equation may be written as dm equal to m in dt plus rg dt minus m out dt minus r cons dt. And integrated from an initial time t equal t0 to a later time tf to obtain t0 to tf tm equal to mt minus mt naught based on this integral equal to m dt t naught to tf r gen dt minus m out dt minus r cons dt. This is the integral balance equation. The left side is the accumulation of the balance quantity in the system between T0 and Tf. The term M in dt is the amount of the balance quantity that enter the system in the infinitesimal interval from T to T plus dt. So that integral T0 to Tf M in dt is the total amount that enter between T0 and Tf, T final. Similar reasoning can be applied to the other terms, leading to the conclusion that equation 10.1-4 is simply another statement of the general balance equation. Accumulation equal to input plus generation minus output minus consumption. Only now each term represents an amount of the balance quantity rather than a rate. For a closed batch system, if the balance quantity is mass as opposed to energy, M in equal to M out equal to 0, and the equation may be written as M initial plus R generation dt equal to M final plus integral R consumption, or initial input plus generation equal to final output plus consumption. This is the form of the integral balance equation given in chapter 4 for a closed system. Example, the water level in the municipal reservoir has been decreasing steadily during a dry spell, and the local meteorologists predict that the drought could continue for another 60 days. The water company estimated the consumption rate in the city is approximately 10 to the power of 11 liter per day. The State Conservation Service estimated rainfall and stream drainage into the reservoir coupled with evaporation from the reservoir should yield a net water input rate of 10 to the power of 6 exponent minus T over 100 liter per day. It is the time in day from the beginning of the drought at which time the reservoir contained an estimated 10 to the power of 9 liter of water. Question A. Write a differential balance on the water in the reservoir. Integrate the balance to calculate the reservoir volume at the end of the 60 days of continued drought. We will write a balance on the mass of system of water in the reservoir mkg but express the equation in terms of volume to make use of the given data. Using the relationship m equal to rho kg per liter V, since water is neither generated nor consumed by chemical reaction in the reservoir, more precisely, we assume that its rates of generation and consumption are negligible. The differential balance equation is accumulation equal to input minus output. dm over dt equal to m in plus r gen minus m out minus r out. Each term in kg per day. dm over dt equal to d over dt rho v equal to rho kg per liter dv over dt liter per day. Since rho is constant, m in equal to rho times 10 to the power 6 e exponent minus t over 100 given by the in the question. The evaporation of reservoir while yield a net water input. M out equal to rho times 10 to the power 7 liter per day, which is the consumption rate. Our generation, our consumption is equal to 0. Water is not produced or consumed in the reservoir. Can cancel rho. dV over dt equal to 10 to the power 6 exponent minus t minus 100 minus exponent minus t over 100 minus 10 to the power 7. At t equal to 0, v equal to 10 to the power 9 liter. Also given in the question at which the time reservoir contains 10 to the power 9 liter of water. This is the balance, differential balance. Next, we conduct integrate the balance. We now separate variable and integrate the differential balance equation from t equal to 0 to t equal to 60 days. So from v naught to v60 dv equal to 0 to 60 days. The expression dt v60 day minus v naught equal to 0 to 60 days 10 to the power of 6 exponent minus t over 100 dt minus 0 to 60 days 10 to the power of 7 dt with v naught equal to 10 to the power of 9 liters. Substitute the integrate the expression and substitute the boundary. We get 4.45 times 10 to the power of 8 liters of water at the end of 60 days of continuous drought. For material balance, total balance necessarily has the form accumulation equal to input minus output. Since mass can neither be generated nor consumed, the accumulation term is always dm over dt, where mt is the mass of the system content. Once you have determined mt by solving the differential balance equation, you may have to verify that the mathematical solution remains within the bound of physical reality, that it does not become negative, for example, or that it does not exceed the total capacity of the system. Example, a 12.5 meter cube tank is being filled with water at a rate of 0.05 meter cube per second. At the moment when the tank contains 1.2 meter cube of water, a leak develops in the bottom of the tank get progressively worse with time. The rate of leakage meter cube per second can be approximated as 0.0025 t, where t is the time from the moment the leak begins. So water enter at 0.05 meter cube per second with volume of the tank is 12.5 meter cube. At T naught V is 1.2 meter cube and the rate of leakage is 0.0025 t meter cube per second. First, write the mass balance on the tank and use it to obtain expression for dV over dt, where V is the volume of water in the tank at any time. Provide an initial condition for the differential equation. Solve the balance equation to obtain an expression for Vt, and draw a plot of V versus T. So balance solution. The total of the mass content is m equal to rho times V, where rho equals to 1000 kg per meter cube is the density of liquid water. Then accumulation equal to d rho V over dt equal to rho dV over dt. The second step follows from the fact that the density of the water is in the tank is independent of transfer may be taken out of the derivative. So constant input equal to rho times 0.05. Output is rho times 0.0025t. Substituting this term into the water balance equation, accumulation equal to input minus output, and cancelling rho yield the differential equation dV over dt 0.05 meter cube per second minus 0.0025t, t equal to 0, V equal to 1.2 meter cube. Verify that each term in the equation, including dV over dt, has unit of meter cube per second. This is the expression. So use the expression to solve the equation. To solve the equation, we separate variable bring dt to the right hand side, integrate from the initial condition t equal to 0, V equal to 1.2 meter cube to an arbitrary time t and corresponding volume V. dV meter cube equal to 0.05 minus 0.0025t dt, integral 1.2 to V and 0 to t for this expression dt. So integrate it, substitute the boundary V. The final expression is V equal to 1.2 meter cube plus 0.05t minus 0.0012 square. Check 1 when t equal to 0, V equal to 1.2 meter cube, confirming the given initial condition. Check 2 dV over dt equal to 0.05 minus 0.0025t. Differential with t will yield the original equation for dV over dt. A plot of the derived expression for Vt is as follows. Initially, the filling caused the volume of water content to increase, but as the leak gets larger, the tank begins to drain. The maximum volume is 1.7 meter cube, well below the tank capacity of 12.5 meter cube. At about t equal to 57 seconds, the content drained completely. The mathematical formula for V predict negative volume after this time, but physically the volume must remain at 0. The liquid discharge as fast as pour in. The actual solution of the equivalent equation is therefore V meter cube equal to 1.2 plus 0.05t minus 0.0012 square for t within the range of 0 to 57 seconds, and after or more than 57 seconds, v equal to 0. The plot shown above should be changed in the range t more than 57 seconds to align coincident with the t-axis. Thank you.